Hello, my name is Rocio Daniela Picos Estelum. My ID number is A017412096. Today, I will be presenting the final challenge for the class of Design and Development of Robots. This last challenge consists of a computed torque control of a two-link manipulator on ROS, and also its simulation. So first of all, what was the goal of this project? The goal was to design and implement a non-linear controller for a two-link manipulator, like what we did previously, but this time for a two-link manipulator. And the method necessary to do this is using a computed torque control or a CTC and using a full dynamical model. For this, of course, we were going to be using Python for our coding of our nodes and ROS and RVs for simulation. So here is the system description. Here's a little picture of how the simulation is supposed to look like and the description of everything that's supposed to do. So it has 2 degrees of freedom, manipulator, 2 rotational joints, and 2 rigid links, like the ones here in this picture. And it has to be modeled using an Euler-Lagrange formulation. I will be talking about it later. And the matrices necessary are going to be the mass matrix, the Coriolis matrix, and the gravity vector, which are implemented in the code that I will explain. And the inputs of our system are going to be the joint torques, and the outputs are going to be the joint position and the velocities in the simulation. So here is a computed torque controller. It's based on feedback linearization, cancels nonlinear dynamics, and applies a PD control on error. And here's a control law that it's going to be used in this case. I will further explain it in the next slide. But the gains are going to be the KP100 and the KD20. So here's a control law. I will explain it. I will explain it better. So here is the complete mathematical equation and everything that it means each variable. So the Q stands for the actual joint angles, and the Q dot is for the actual joint velocities, of course, because it's a derivative. And then the QD, Q dot D, and Q double dot D are the desired position, velocity, and acceleration trajectories of our model. The MQ is the inertia matrix. The CQ and Q dot are the Coriolis and centrifugal matrix, and the GQ is the gravity vector. Lastly, KP and KD are the proportional and derivative gain matrices. So then I implemented all of this previously stated on ROS. The node 1 is the one that simulates the manipulator dynamics. The name is DLM dynamic sim.py. Node 2 implements the CTC controller and CDC underscore control.py. The topics is joint states, which publishes the joint position and velocities, and DLM input, which subscribes to torque commands, and it runs at 200 Hertz. And the simulation results, then we're going to be moving to ROS to explain all of this in a second, but simulation result is a reference to sinusoidal trajectory for both joints, of course, the shown movement that the DLM is going to have on simulation and RVs. And the output is a manipulator that follows a reference closely, and the result is high tracking accuracy and system stability. So then next I will be showing everything on ROS. Here it is. Here is the Visual Studio. Here is the DLM dynamic simulation. This code was already given by our professor. So here it wasn't necessary to change anything. It has the parameters of the DLM and the set of parameters of the simulation, the variables to be used, the input message, the process output message, subscribers, publishers, callback function, the main run function system, the defined to define sampling time and dynamical system simulation. Here are all the equations necessary for the correct functioning of our simulation. Then the message to publish, for the robot joins are harder stamp, and then the published message. And here it is everything. I will going to move to the other node. So here is where we use all of the previous models that I explained in the presentation. Here we define the global variables, the callback subscriber, the physics parameters of the system, everything previously stated, and then the configuration of the output message, everything here. Next is inside of the while loop. We generate the desired trajectory with all of the parameters that I previously defined and stated. The PD control, the states of the system, and the two matrices and the vector that I already mentioned, which are the inertia matrix, the centrifugate and Coriolis matrix, and then the gravity vector. And lastly, here is a control law that I previously explained, the mathematical equation, and all of the things that I already described previously. But after having these two nodes and then the launch files, I launched that on the terminal. Here it is. I did a catkin make. Here, a catkin make, then a source eval, and a ROS launch. And lastly, here is the simulation on RVs. You can see here how the movement is like a waving movement, moving from left to right and vice versa, but slowly and only up to a certain point. After it reaches that point, then it goes back to the other position because of the sinusoidal movement that it's supposed to be having. But that is it, and that's everything regarding my final challenge. So thank you for your attention.